Here I'm forming images of the sun with a 50mm focal length lens. I gotta be careful doing this. That's much too bright to look at with your eye. I was looking at it through the camera that was recording the video. How bright is it is the important question we want to talk about in today's episode. The sun, of course, is illuminating Earth with energy equal to the solar constant, 1300 watts per square meter. So that's what's illuminating the aperture here. Now that aperture distribution is turned into this focus spot, and the size of the focus spot is the angular extent of the sun times the focal length, which in this case would be about half a millimeter. So we've gone from 50 millimeters or so on the aperture to half millimeter at the focus, an increase of in the energy density by a factor of around 10,000. The increase is going to be 1 over delta theta squared times the f number squared. So it's about 10,000 for the 1 over delta theta squared, and then that could be reduced by a factor of 4, so based on the f number, to maybe 2,500 times brighter than what you see without the lens. So what you'd expect is that the white part of the tissue here that's not going through the lens is about 2,500 times less intense than the focus spot. We want to talk today about how to translate this into the signal we'll get in a digital camera. For a long time, photographers used light meters to figure out how much light they were going to get on their imaging systems, and so they would take one of these Weston light meters, for example, and hold it up next to the subject and get an idea of what was the illumination energy, and then they had to translate that into the amount of energy that they would get on their film. Of course, today we don't need light meters because we have active pixel sensors that can measure directly how much light they're getting. We don't get one shot. The photographer back in the film days had to get the exposure right, or he'd wasted some film, but we don't have to worry about that today. But we do want to worry about how much exposure we should use to record the film, and in order to understand that, we need to understand how the illumination translates into signal on the focal plane. For a long time, this was done with film speed ratings. You had the ASA rating. Maybe even before ASA, the Weston company had their own film ratings based on their light meters. Today, we want to talk about, in digital cameras, what signal we should expect for a given illumination and how to understand how much energy there is in the recorded image. Computational Imaging. Episode 59, the camera equation. So we're interested today in talking about radiative transfer. How much of the light hitting an object goes to the focal plane of an imaging system, and how do we figure out what is the intensity at the focal plane? We're going to use a little bit of terms of radiometry. I'm borrowing some notation here from John Grievenkamp's Field Guide to Geometric Optics. So L is going to be the radiance. It's the energy in watts, or the power in watts per meter squared per steradian, illuminating the object that we're trying to image. We've seen radiance before in this course. Back in episode 54, we talked about radiance tomography, and we defined the generalized radiance as the Fourier transform of the cross-spectral density, where S is the direction of propagation of the field and X is the spatial position. And because we have a partially coherent field when W of delta X is not delta correlated with respect to delta X, that means that the field is propagating in a direction. An incoherent field emits in all directions. Any field that's propagating in some defined direction will be partially coherent, and that translates into a directional radiance, as we've seen here. Returning to our imaging situation, let's assume that the radiance illuminating the object is L of X and theta. And so X here is going to be a position on the object, and theta is going to be the direction of the optical axis toward the camera. So in the angular extent going into the focal plane through the camera. Now on the object we have a ground sample distance D. So this is the extent covered by 1 pixel in the focal plane on the object. So for each pixel, we can image the pixel onto the object, and that's our ground sample distance D. The energy collected from the object by the imaging system is related to the solid angle captured by the imaging system, which is going to be the diameter of the aperture divided by r squared times this pi over 2. So this is the solid angle collected by this imaging system going into this pixel. So if we want the total energy collected from that ground sample by the imaging system, that's going to be the reflectance rho of the object times the ground sample distance, or the ground sample distance squared, so that's the area of one pixel on the object, times the radiance of the object times the solid angle collected by the imaging system. So this energy goes on to that one pixel. Now if we want the energy density on the pixel, we would divide that by the pixel area delta squared. So this is the irradiance hitting the pixel, the energy per unit area squared on that pixel on the sensor. Now we know that d over r, the ground sample distance divided by the range, is equal to delta over f by simple imaging, ray tracing. And so we can replace the d over r in this energy hitting the pixel by delta over f. The delta squared will cancel then, and we'll get that the intensity, the energy, the irradiance, the energy per unit area striking the focal plane is the reflectance of the object times this a squared over f squared times the radiance of the object. Now the f over a, of course, is the f number. So this 1 over f is basically the numerical aperture. So we're basically saying that the energy hitting one pixel is the radiance of the object times the sterradians in the numerical aperture and sterradians in the numerical aperture squared. So this result is known as the camera equation. It tells us, given the radiance hitting the object, what the energy per unit area is going to be on the sensor. Now, a lot of times we can assume that L is constant. We have this idea of a Lambertian radiance, where L takes a simple form of the intensity times cosine of theta divided by pi. So this is for a standard diffuse reflector model for what the reflected radiance is. And in that case, we can remove the angular dependence and just assume that theta is equal to 0 in the direction of propagation toward the object. Of course, theta could have some tilt in general, but we assume it's a constant. And so then we get the simple form of the camera equation that the irradiance, the energy per unit area squared striking the focal plane, is the irradiance striking the object. I naught would be the illumination irradiance on the object, times the reflectance divided by the f number squared. So if we had an F1 system, amazingly enough, the irradiance on the focal plane is equal to the irradiance on the object, independent of how far away the object is. That has to do with the magnification. So of course, the total energy collected by the lens is much less than the energy emitted by the object, but because the lens focuses the scene to a demagnified object, the intensity can be the same as it is on the object. So this is why looking at the sun is so dangerous, because the energy intensity of an image of the sun is equal to the energy intensity on the surface of the sun divided by the focal f number squared. So basically looking at the same energy as you'd see on the surface of the sun in the image of the sun. Continuing with this solar example, the radiance of the sun on Earth is about 20 million watts per meter squared per sterradian. We get that roughly by taking the solar constant, which is just 1300 watts per meter squared, and dividing it by the solid angle of the sun, and it increases it by about a factor of 20,000. For a Lambertian reflector illuminated by the sun, the camera equation tells us that the irradiance that we're going to get at the focal plane is going to be the irradiance of the sun, the solar constant, times the reflectance divided by the f number squared. If we think about having a camera, for example, with a 1.5 micron pixel, and we're going to expose for 30 milliseconds, this result would tell us that we could expect 2 to 5 million photons, depending on what's the reflectance of the object and what the f number of the lens is. In contrast, if we went for a specular reflector, the camera equation would tell us that the energy on the pixel would be proportional to the radiance of the sun, which is 10,000 times brighter, which is why you get this much brighter reflectance when we look at specular reflectance from the sun. Now, the important thing to recognize is that this is not infinite. There's a finite number we can calculate for how many photons we're going to get from different sources, and the camera equation is a simple way. If we measure the irradiance on the surface of an object, we can calculate what the irradiance we're going to get on the focal plane is, and similarly, if we measure the radiance of the object, we have a good idea of what we're going to measure. Just as a continuing this example, here's a look from 33 miles away from a mountain in Tucson, looking to the road up to Mount Lemmon. Here's through a telescope. We're looking at the natural diffuse reflection of objects, and then here is actually a about 2-inch across object that's being rotated by hand, and you can see this bright flash. That bright flash is not infinitely bright. It's somewhere in the range of 10,000 times brighter than a single pixel, and so that bright flash is coming from less than 1 pixel, but it blooms out to something bigger because of the turbulence of the atmosphere and the blooming in the camera. As we saw in our discussion of radiance tomography, there's amazing things to be found by analyzing the specular reflections in scenes. Here's from the same viewpoint where we saw that flash of a reflector being rotated. We're looking at some cars driving down the Mount Lemmon Highway 33 miles away from Tucson. And you can see these bright flashes from the specular reflection off the windshield of the cars. But again, the main point of today's episode is to just understand how we can relate the illumination of an object in radiance or irradiance to the signal we're going to get on a focal plane through the camera equation. Next time, we're going to talk a little bit about camera calibration. This course, these episodes are on the physical nature of optical measurement and computational imaging system design. This is not a course in computer vision, so when we talk about camera calibration, we're not going to get into all kinds of detail about distortion and other things that are purely geometric. Those features are the topic of computer vision, so we're not studying image processing, we're not studying computer vision. Professor Sri Nair from Columbia has this wonderful series of YouTube videos talking about principles of computer vision that can go into a lot more detail about camera calibration. We're going to just focus on understanding how we can calibrate the features of the physical forms we've talked about, and especially how we can measure the actual optical transfer function of a lens by analyzing images. And we'll get to that in the next episode.